so much for the invite. I'm really honored to be here today and talk to you guys about minerals and gemology. About myself, I'm a lifelong mineral lover. I've known since like maybe 5, 6, 7 years old that I wanted to be a mineralogist when I grew up. It's kind of like it's in my blood. So I'm really fortunate to have been able to like follow that mineralogical passion of mine and end up actually being a mineralogist when I grew up. And I also want to say I'm really fortunate to have ended up at a place like GIA, the Gemological Institute of America. Um, Although I may not have realized it when I was, 5 or 6 years old, that gemology was like really the best way for me to pursue this mineralogical passion of mine. And so I realized, when I was younger, I didn't realize the connection between mineralogy and gemology. So that's kind of one of the things I want to just talk about today, and maybe hopefully share that connection with you guys. So if there's any budding mineralogist out there, maybe you'll consider gemology as a potential path forward for, advancing mineralogy and studying mineralogy. So the talk I'm going to give today is Gemstones, Time Capsules Connecting Us Through History. And my name is Aaron Palke. I'm a Senior Manager of Research at the Gemological Institute in Carlsbad. And I'm talking here for Minerals Day of Earth Science Week. So I'll start off with some just basic groundwork. What is a gem? Now, I've been in gemology for about 5 years now, so I think I know a gem when I see one, but I realize also the definition of a gem is somewhat subjective. So let's cover some groundwork here. A gem is basically a material, any material used for personal adornment. Typically, it's natural, maybe lab-grown, inorganic, organic. Again, that's somewhat vague. So maybe we can also just break down a little bit more further. This is any pretty stone that you can wear. Again, that's somewhat subjective because pretty is kind of depends on who's looking at the stone. But I think most people know a gem when you see one, right? So what does this have to do with mineralogy though? And I guess the simple answer is that most gemstones are minerals. Now to address that though, we kind of have to talk about what a mineral is, of course. So according to the standard definition of a mineral that's accepted by the mineralogical community, a mineral is some material that satisfies these three basic requirements. It has to be naturally occurring, it has to have a crystal structure, and it has to have a definite chemical composition. And like I said, most gems are going to be minerals, and I'm going to tell you, I guess, why. So for the first part, a mineral has to be naturally occurring. This basically means that a mineral has to have formed in the earth through geological processes without direct involvement of humans or life forms, essentially. There are some gray areas with this. There are some instances where there might have been some indirect involvement of humans in terms of some mineral species that have been approved as valid mineral species. But for the most part, I think people pretty much know what this means, right? As a mineral is something that forms in the earth through geological processes, and most gemstones are actually minerals in this sense. Most of the treasured rubies, sapphires, emeralds, and diamonds, they're all naturally occurring stones that we derive from the earth. Now, the second condition, of course, is that it has to have a crystal structure. We have certain gem species like rubies and sapphires and tanzanite and emeralds that you may not realize it, but these are also minerals because the gem species name hides the mineral name, which is corundum, zoisite, or beryl. And these gem species have the same crystalline structure that these mineral species have. So if we look at these gem species, they have the same ordered internal structure, periodically repeating crystalline arrangement of their atoms in that structure. Now, finally, a mineral has to have a definite chemical composition, and most gemstones will satisfy this requirement as well. So I'm showing here as an example, these two photographs that I'm showing, it's a ruby and a sapphire. So these rubies and sapphires, these are the mineral corundum, and corundum has the definite chemical composition of Al2O3, which means you have 2 atoms of aluminum for every 3 atoms of oxygen. And that's shown also schematically in the crystal structure diagram I have there, where the blue spheres are representing aluminum atoms and the red spheres are representing oxygen atoms. And so if you took time to count all the atoms in that structure, you'd find 2 atoms of aluminum per 3 atoms of oxygen. Now we say definite and not a fixed chemical composition because this allows some variability in the chemical composition. So for instance, a pure corundum crystal with only aluminum and oxygen atoms would be colorless. There'd be no color to it. And especially with stones like ruby and sapphire, color is really the most important factor in determining the value of those stones. So a pure corundum crystal wouldn't be as nice to look at as a ruby and sapphire. So how do we get the ruby and sapphire? Well, you take a little bit of those aluminum atoms, remove them from the structure, and replace them with something else. So for ruby, replace the aluminum with chromium. And for blue sapphire, we replace some of those aluminum atoms with iron and titanium atoms. When you have iron titanium in pairs, you produce a nice blue color because those iron titanium pairs absorb certain wavelengths of light and let the blue light coming through the stone. So this is what we mean by definite chemical composition. We can define the chemical composition as aluminum Al2O3 with some variability, allowing for color to be produced in certain gemstones. So that's kind of the basic connection between the mineral and the gem world. But you still might be wondering why we're talking about gemstones on Mineral Day, right? So I think to get at that, I want to maybe just ask a few questions that a gemologist might be asking in his or her daily work. So one of the basic fundamental questions a gemologist asks is, what is it? So let's say someone hands you a beautiful faceted red stone, a beautiful faceted red gemstone, and you look at the stone, it's got this amazing rich red color, the best red color you've ever seen, better than any ruby you've ever seen in your entire life. Now, you might be thinking this must be a ruby because of the nice red color. But as a mineralogist, we also know that basically you can't identify a mineral based on its color alone. And this is where these connections start to happen, because one of the ways that gemologists start to address these questions of what is it a ruby, or is it a spinel or a garnet or some other red colored gemstone? Gemologists borrowed a lot of knowledge from the mineralogical community in order to answer questions like this. So if we had that red gemstone, we needed to identify it. What we could do is look at some of the basic mineralogical properties of that gemstone. We could do what mineralogists have been doing for hundreds of years. We can measure the refractive index of the gemstone. We can measure its density, its hardness, or look for cleavage on certain cracks or fractures around the stone. We could look at the birefringence of the gemstone. We could look into a microscope and look at inclusions and other things inside the gemstone. And so all of these concepts that the gemologists use to identify stones, is it a ruby or a garnet? These are all concepts we borrowed from the mineralogy world. And a lot of those basic mineralogical properties have done an enormous amount of work to identifying just what is the gemstone. What is the basic gem species or mineral species of the gem you're looking at? Now, as soon as we started taking those mineralogical properties and using them to answer the question of what is it, all of a sudden things started getting a little more difficult, especially in the 20th century when our technology started advancing. And all of a sudden, our gemstones came not only from the earth, but also from laboratories. One of the big things in the 20th century was the rise of laboratory-grown gemstones. So people have figured out how to use advanced technology to grow big, beautiful crystals of rubies, sapphires, emeralds, diamonds, almost anything you can imagine. People learned how to grow those stones in the lab and create analogs, lab-grown analogs to the natural stones we'd been mining and pulling out of the earth for a long time. And this became another big problem in gemology, and we had to look for new ways to address this question as well. And so again, we used mineralogical properties, mineralogical knowledge to address this question as well of, is it natural? So one thing we could look at is mineral assemblages. So if you found a ruby in the ground in the earth, you could look for other minerals that are associated with that ruby, like this photo here of a marble-hosted ruby. It grows in a rock we call marble, which is composed dominantly of this mineral calcite. And so what you could do then with this knowledge, you could look inside the ruby, a faceted ruby, with your microscope. And if you saw, like this photomicrograph shows in the bottom center, these are inclusions of calcite in a ruby. And so if you see inclusions of calcite in the ruby, that's a good indication you have a natural stone, because you can correlate this to the marble-hosted ruby that you found, that you pulled out of the ground, and you saw that it came out of the ground as a natural ruby. Now, identifying lab-grown stones was much the same. We looked in a microscope at the ruby, and we looked for inclusions inside this ruby to correlate it to the conditions of formation. In the case of a lab-grown ruby, most of the lab-grown rubies are created by a process called the flame fusion method, where you take alumina powder and you melt it with a high-temperature torch, drop it onto a pedestal that's turning and dropping down as the molten corundum is falling on it, and you crystallize these big boules of ruby or sapphire. And so some of the things you might look for here are gas bubbles inside the ruby with a microscope. And you might see curved striae from the process where the ruby is turning as it's cooling and slowly crystallizing. So again, we use our mineralogical knowledge of how these stones form to get an idea of how to separate these lab-grown and natural stones. And while this is, I mentioned, these lab-grown stones is sort of a modern challenge in gemology, but I also want to dig back a little deeper and point out that gemology is sort of an ancient tradition as well. It's not something new in terms of identifying what a stone is, what your gemstone is, so that you know how to properly sell it and set it in jewelry and all this other stuff, is something humans have been thinking about for a long time. As an example, these are two photographs of Roman jewelry with glass in them. And so the Romans actually were pretty good at creating glass and using glass, artificial man-made glass, as gemstones. And in some cases, they were using the glass as glass, so they intended to use it in jewelry as glass. But in some cases, these pieces of glass, the man-made material, could have been used as an imitation for more valuable natural stones as well. And so this is something people have been dealing with for millennia, for hundreds and thousands of years. How do we separate natural stones from man-made stones or imitations and other problems in the gemology world? And it's more than this, though. So people have been looking at gemstones for a long time, asking questions like this: what is it? But I also want to make the point that gemstones have been a view into the geological evolution of the earth from the moment that people started looking at gems to the modern day. A great example of this is amber. And actually, if you look at some of the other gemstones people deal with, some of the ancient stories, the origin stories of their formation, can often be a little bit bizarre and essentially kind of just wrong from our modern geological understanding of the earth. Some of the ancient philosophers and natural historians had some pretty strange ideas of how gemstones formed in the earth. But one of the things that these ancient philosophers and natural historians got right was amber. And although amber is not actually a mineral, it is a very valuable gemstone. And it's a view of how people started using gemstones to look into the earth processes. So people might have taken a piece of amber and looked at the inclusions. So inclusions of bugs and insects. They might have noticed that when you rub it gently, you might get an aroma that was reminiscent of tree sap. And so people pieced all this information together, all this gemological information, they pieced it together to correctly surmise that amber is basically fossilized tree sap that may have, when it was flowing, it may have trapped insects and bugs inside of it and fossilized those insects and bugs in it as well. And so from the very first time people started looking at gems, they used gemstones as a clues to the earth history. And we're doing this still today. And we're doing it in a little more sophisticated ways in some cases. One great example is inclusions in diamonds. These photomicrographs I'm showing are inclusions in diamonds, garnets, and clinopyroxene inclusions in diamonds. They're all very, very small. You have to use a microscope to see these. They're all less than one millimeter in size, these inclusions. But they give us a great clue into the geological evolution of the earth and the composition of the earth. And the reason this is so valuable is that diamonds come from this part of the earth called the mantle. And so we all live on the earth's crust, the top maybe 30 to 50 kilometers of the earth, the solid earth. And below that is the mantle. But the mantle is basically this big, inaccessible portion of the earth. We can't really go and directly sample the mantle. You can't take an elevator shaft down to the earth's mantle, chop off a rock from the mantle and bring it back up to study. So we have to rely on other methods for studying the earth's mantle. And one of the great things of gemology is that diamonds are just that sort of time capsule from the earth's mantle. Diamonds come up in these violent volcanic eruptions of kimberlite eruptions, in which these magmas coming down from the earth's mantle bring up little bits of the earth's mantle along with it as it's being erupted onto the earth. And so we take these diamonds, these little pieces of the earth's mantle, and we can look further inside the diamonds and look at the inclusions in them and get a very good idea of the composition of the mantle and processes going on in the earth's mantle, and look at the evolution of the earth's mantle and the earth at large over the entire history of the earth. Now, another question that a gemologist might ask is, has it been treated? So even this is also an ancient question as well, because people, as long as we've been using gemstones, people have been trying to find ways to enhance the value of those gemstones artificially. And a great example of this are sapphires from the state of Montana in the United States of America. So these Montana sapphires, and both of these photographs show Montana sapphires. On the left are some unheated sapphires in their rough state. These are sort of typical colors you might get from these deposits. And on the right are heat-treated sapphires. So these are sapphires that have been taken from the photo on the left and heated at high temperature in order to enhance the blue coloration in these stones. And it became important to be able to identify these heat-treated stones compared to the unheated stones, because there's certain values ascribed to the heated versus unheated stones in the marketplace. And so as a gemologist, I would again turn to the book of mineralogy and take some of their playbooks and apply that to this problem as well. So the first thing I would look at is the microscope. I would look at a stone in the microscope and I would look at its inclusions. And I would try to understand if these are natural looking inclusions or if they have been altered in some way by artificial heat treatment. For an unheated sapphire from Montana, I would look for this, what we call rutile silk. So these are very minute inclusions of rutile, titanium oxide, another mineral inside the corundum. And they form these long, slender needles in many cases. And if you found these rutile silk, these needles of rutile unbroken and in this sort of pristine looking condition, that would be a good indication that the stone had not been heated. Now, we could look at a heated stone as well, a heated Montana sapphire. And if you saw an inclusion scene like this, looking in the microscope at your sapphire, you'd have to be very careful. So what we see with this inclusion scene are inclusions of rutile that are surrounded by these blue halos. So it almost looks like this blue color has been leaking out from these rutile inclusions in the sapphire. And essentially what's happening is that the stones have been heated in order to take the titanium from those rutile inclusions, dissolve it into the crystal lattice of corundum. And if you can create iron titanium pairs in the corundum crystal lattice, you create this rich, vivid blue color. And we can see, obviously, this is not a natural looking inclusion scene. You would never see this in a natural untreated sapphire. And so we use these mineralogical concepts and mineralogical techniques to answer questions like this as well. Now, one really interesting question that modern gemologists ask is, where is it from? And this is something that's become a much bigger question in the last couple of decades in the gemology world. So the essential question is, if you had a ruby, do you want a Burmese ruby or a Mozambican ruby? It's all of a sudden it's become important to know not only what the stone is, has it been heated or unheated, but also where that stone came from in a geographical sense. So would you rather have a Burmese ruby from the fabled deposit in Mogok, the deposit that's been producing beautiful rubies for more than 800 years? Or would you rather have the Mozambican ruby from the deposit in East Africa, the big deposit that's come up in the last 10 years, is the biggest deposit in the 20th century, the biggest gemstone discovery in the 20th century. And this became a really difficult problem in gemology. The rubies from these deposits, that are the same mineral, of course, they have, in many cases, the same physical properties. And so we have to use more advanced mineralogical techniques and more advanced analytical techniques in order to get even further, more fine-scale information about these stones, to try to find some kind of fingerprint to correlate them to these different deposits around the world. Now, one thing I'm going to just talk about briefly is this technique we call laser ablation inductively coupled plasma mass spectrometry. And I know that's a mouthful. We sometimes call it LAICPMS. It's this instrument I'm showing here. There's a laser ablation unit on the right part of this photograph, and then there's an inductively coupled plasma mass spectrometer on the left part of the photograph. Essentially what we do is we would take this sapphire, we would put it into the laser ablation chamber, and around the outside edge of the stone, we call the outside edge of the stone the girdle. And I'm showing you a photomicrograph of the girdle of the stone, the outside edge, and you can see these little pits that have been created in this stone on its outside edge. And I made these little pits in this stone using an ultraviolet laser. These pits are about 50 microns wide, essentially about the width of a human hair wide. You'll never see it in the stone unless you really go looking in a microscope. But basically what I've done is I've used a laser to ablate a little bit of material, to remove a little bit of material from the girdle of the stone. And I take that material and I send it through the mass spectrometer, the other part of this LAICPMS instrument, And the mass spectrometer is capable of separating all the atoms in that material based on their mass. And so we can essentially get a sampling of the entire periodic table, all of the elements in the periodic table. We can measure the chemistry of this stone very precisely using this technique called laser ablation ICP-MS. And here's an example of why we do this. So what we want to do with this technique is find some kind of chemical fingerprint to separate stones from different deposits. This is an example of a stone we call Paraíba tourmaline. It's the mineral elbaite, or sometimes lidocodite. It's a tourmaline that is colored by the trace element copper. And so you put copper in these tourmalines and you create this rich, vivid green to blue color. And it was originally found in the state of Paraíba in Brazil, but they subsequently found stones, the same types of stones, in Nigeria and Mozambique. They all can look fairly similar, but the trade wanted to know, the gemstone trade wanted to know where these stones came from when they were selling them. And so we use this technique to measure the trace element chemistry of these tourmalines, and we create a chemical fingerprint. We use elements like copper, gallium, lead, strontium to create a fingerprint to compare the stone that we're looking at with our reference database to determine if this is a Brazilian, Nigerian, or Mozambican Paraíba tourmaline. And actually, this is really one of the interesting things about being a gemologist and being in the gem lab, is it always fascinates me because we have this mixture of these classical, traditional analytical techniques like a microscope, and we mix that with all these advanced analytical techniques like laser ablation ICP-MS, all types of spectroscopy where we measure the interaction of electromagnetic radiation with the gemstone. And what we find is that these old traditional techniques are just as important in the lab as these modern advanced analytical techniques. And so for any day I might be going from looking at a stone in the microscope to blasting the girdle with a small laser to ablate material and put it through a mass spectrometer. And all of these techniques have to work hand in hand to help us address these questions in gemology. Now, one of the other really interesting and maybe the best aspects of gemology for me is going out into the field. Most of my work is done in the lab. I spend 10 months out of the year in the lab, if not more. But we have these trips that we take out into the field. And in modern times, we've realized that we really have to couple the information we get in the lab with information we can collect out in the field. So what we do is we send our gemologists out in the field to get as close to the gem mines as possible, to go visit these gem mines, to collect information and to collect samples. This is a photograph of an expedition we took to Mogok in Myanmar, which is one of the famous ruby and sapphire producing regions in the world. And we went there to collect samples and to see what was coming out of the ground. And so this is really big in terms of providing information for our origin determination services. If we want to be able to trace stones back to their geographic origin, we need to have reliable reference samples from those origins. So we go out in the field and collect samples. This is a photograph of a demantoid garnet mining operation in the Russian Urals near the town of Yekaterinburg. And it's not only collecting samples, it's also just collecting information. We go into the field and we look for what stones are coming out of the ground, how many stones are coming out of the ground, what are their qualities, where are the stones going after that. And this all helps us provide more information for us to use in the lab when we have difficult stones to deal with. So I'm kind of getting toward the end of the presentation today. I want to kind of just talk about why you guys should care about gemology. I hope I've impressed upon you guys that a mineralogist should care about gemology in some level. And I hope I've also made the point that gemology could be a good career path for you guys in the future. It could be something to pursue. I was fortunate enough to become a gemological researcher at one of the biggest gemological institutes in the world. A lot of the guys I work with in the lab are gemologists. So these are the guys who work with the stones every day. And I've gone around and talked to a lot of them, and maybe like 90% of the lab gemologists that I work with, 90% of them are probably geologists or mineralogists in their backgrounds. And so this really just goes to show that all the information you get, all the techniques you use as a geologist or a mineralogist can be really applied very well to gemological questions as well. Actually, I took a year as well as a museum curator, and that could be another great way to get involved in gemological or mineralogical research, using these big collections that have been built up over years to find the best way to utilize those as research tools and also as educational tools for the public. Now, there are also career paths forward for gemologists who may not be involved directly in the lab or in research. Even just career paths like gem and jewelry sales or gemstone cutting, jewelry design. These are all career paths in which it can be very useful to have a good mineralogical and gemological background in order to communicate with your clients, in order to know what kinds of stones you're dealing with, in order to know how to navigate your career very successfully. It can be very useful to know a lot about gemology and mineralogy. And I just want to say, if this sounds interesting to you at all, if a career in gemology is appealing to you, GIA does offer some educational programs that provide practical training for careers in the retail jewelry industry. We have campuses all around the world with instructors who give hands-on experience in the lab and through other educational avenues to learn more about gemstones and to earn diplomas in many cases for colored stones, diamonds, and jewelry design. If this is interesting to you guys, I urge you to go to our website, www.gia.edu, to get more information about our educational programs that might be available to you. Now, if you don't want to go fully down that path of an education in gemology, but you just want to know a little more about gemstones, there's a lot of other good information on our website, gia.edu. One thing I want to highlight is our Knowledge Rocks emails, where every week we'll send you an email with great information from the lab, from our library, and from our researchers about the gemstone world. And if you want to sign up for this, go to our website, scroll toward the bottom of the page, and there's this button you can click to subscribe to the Knowledge Rocks email. And one final thing I want to note is our Gems and Gemology quarterly journal. It's our quarterly journal. We've had it for over 80 years, and it contains all of this wealth of information that we've learned over this 80-year period, all of the research and everything we've done. We publish in this journal, Gems and Gemology, and it's all available online free of charge. So if you want more information about gemstones, please feel free to go to the site, gi.edu, gems-gemology, to download any issue you want and learn more about gemstones. And with that, I thank you guys for your attention, and I hope you guys have piqued your interest a little bit in terms of gemstones and learning about how gemstones are related to the mineral world. So thanks so much, guys.